Oh, hello everybody. Welcome to Lecture 27 of Thermodynamics. Today I'm going to be talking about the second law still and finishing up our work on this chapter. And hopefully by the end of today we'll have finished with chapter 5 and we'll be moving on to chapter 6 on Monday. So I know there's a lot going on with chapter 2 and hopefully you found the discussion really interesting. I actually came up with the two. You can blame me for coming up with the two example problems on perpetual motion machines, Maxwell's Demon and the zero motor. Both of those things were actually invented, things that somebody actually came up with and as a thought experiment, and in case of the zero motor, something that somebody actually thought was going to work and tried to build, right? So many a perpetual motion machine. It was actually tricky to come up with easy examples of perpetual motion machines of the second kind. Those are the ones that violate the second law of thermodynamics, but don't necessarily violate the first law of thermodynamics. Most perpetual motion machines that we see violate the first law, and then there are those, of course, that are pretty easy to find or to identify. But the ones that violate the second law are a little trickier and they're pretty nuanced. So I went through and found a couple of the more obvious ones that you could analyze. So hopefully that was interesting, and hopefully Ollie was good at explaining those things to you guys. So today I'm going to talk a little bit about the rest of the sort of the background of the second law, right? And talk a little bit about the Clausius inequality, which is the basis for the second law balance, if you will, or the entropy balance. But first, let's talk a little bit about the survey from yesterday, from Wednesday. For an ideal reversible cycle operating between two reservoirs, thermal reservoirs, what is the ratio QC to QH equivalent to? So most everybody got this right. You could look at my slides and you can get this off pretty quickly. So this is the ratio of temperature of the cold reservoir to temperature of the hot reservoir. It's not the opposite of that, and it's not the work ratio. The work ratio means nothing, and I'm glad that nobody chose infinity. That was just the silliest thing I could come up with. And so, yeah. So anyways, you got it. And I think most people understood this one. So yeah, I'll as usual, be posting another survey for you to do tomorrow and on Friday. And hopefully that all, gets that you can get to it. And it seems like it's working pretty well. So great. Let's see. Let's keep on going. Next thing that we usually do is start looking at the slides here. So as we said, all right, this is where we were with the Carnot power cycle. Remember, we talked about the Carnot cycle. We're going to do an example. We're going to do 3 examples today, and they all kind of have to do with different parts of the second law and using these equations. Really, the main thing that we're getting to is that this maximum efficiency of a Carnot cycle or an ideal power cycle is equal to 1 minus Tc over Th. And for refrigeration cycle, the maximum power, the maximum efficiency is also given by the temperature ratio as well. Okay, so yeah, we did this example Wednesday. So here we are, kind of refrigeration in heat pumps. So if a Carnot cycle is operated, Carnot cycle is operated in the opposite direction, the magnitudes of all the energy transfers remain the same, but the energy transfers are oppositely directed. So this is the case of a refrigeration cycle. Such a cycle may be regarded as a Carnot refrigeration or heat pump cycle, for which the coefficient of performance, the maximum coefficient of performance, is given by this beta max equals Tc over Th minus Tc, or the Carnot heat pump, which is Th over Th minus Tc. Notice that all we did was replace the Q's with the T's. All right, as I said, you can't always do this whenever you have some cycle. You can't just decide to replace the Q's with the T's. But in the case of an ideal cycle, you can do this because that's how we define the Kelvin temperature scale. If that's confusing to you, go back and try to read in the textbook a little bit. There's some more detailed information given in the textbook that you can look at and understand where and how we derive that. But for now, I mean, it's just safe to say that if you are asked what the ideal thermal efficiency of a power cycle is, it's 1 minus T C over TH. And likewise, the Carnot refrigeration cycle is beta max equals TC over TH minus TC, because TC is representative of QC, the Q that you're trying to get from the cooling cycle. And the heat pump is obviously the opposite. You're trying to get the hot energy, the hot heat stream, the QH, which is, in this case, proportional to the TH. Okay? All right, so this is how we do the ideal refrigeration cycle. Now, I'm going to do an example of a couple of these things just to start us off and get, let's get my iPad here going, and we'll get this thing started. So let me just go to the iPad itself. Okay, let's do example 1. Okay, so here we are. So we're going to talk, the first example we're going to do is about refrigeration cycle, ideal refrigeration cycle. And then the second one we're going to do is about the Carnot cycle. But these are all kind of the same thing, right? I mean, essentially we're talking about ideal cycles, ideal thermodynamic cycles. Okay, so this one says, a heating system must maintain the interior of a building at 20 degrees C during a period when the outside air temperature is 5 degrees C and the heat transfer from the building through the roof and walls is given 3 times 10 to the 6 kilojoules. That's a lot of energy. Okay, must be a big building. Okay, 3 times 10 to the 6 kilojoules. All right. That'd be 3,000 megajoules. For this duty, heat pumps are generally a consideration that would operate between the dwelling and A, the ground, B, a pond at 10 degrees C, and the outside air temperature at 5 degrees C. For each case, evaluate the minimum theoretical net work required for any such heat pump in kilojoules. All right, so we're trying to maintain the building. We're trying to heat the building using these outside air temperatures, okay? So let's just do that here. Okay, so in this case, yeah, so what's known? Well, what's known is that we have 3, well, we'll just say operating data for 3 heat pumps. Use the heat the outside air from heat the building from using cold outside ambience, either the ground, the pond, or the outside air. Okay, so we're supposed to find. We're going to find the theoretical work required. All right, so we're trying to find the minimum. So this is an interesting exercise as an engineer, just as an aside before I get going with this. So if you're an engineer and somebody has an idea, like for instance, you are an energy engineer and somebody says, hey, what if we decided not to use a furnace and instead to heat our building using a heat pump? And you would say, that's an interesting idea. Well, let me figure out what the minimum required work is. Because maybe it's possible that the minimum required work is more than you're willing to spend. It could be more costly. For instance, if you have to provide that as some sort of compressor work, as opposed in an electricity cost to run a compressor versus how much it would cost to run that as a furnace, like how much the gas cost would be to just use a furnace and directly heat the building, right? So I don't know, outside air temperature 5 degrees C, that's not so bad. If it's Minnesota, then you're talking negative 20. It might be too much work. Just the electricity cost might be too high in order to get that done. All right. Anyways, that's all I'm saying. Okay, so the diagram here, let's see. Let me make we'll do some assumptions first. So let's do our assumptions first. The first thing we're going to say is so we're going to say we have a steady state. I guess reversible heat pump. And we'll say that the ground, pond, etc., blah, blah, air are ideal thermal, thermal reservoirs. Okay, so I guess that's all we need to do, right? Okay, so then let's do a diagram. So the diagram looks like this. We got some big building, right? And we've got a heat pump that's going to take some QC, either from whatever it is. I don't know. It could be from the pond, or there's different places. You have 3 different locations you could be taking from: A, B, and C, right? So, and then you're going through here, you're going to put some work into this thing, because you have to put work in, right, to move QC you have to put work in to move QC to Q it to from TC to T to TH. And so this is TH, this is the building, and it's at TH, right? And this is TC, whatever thermal reservoir this is over here, right? So this is our diagram, and this is our thermodynamic system. And this is QH. Okay? This is our system. Always good to label your system, put the dotted line around it, no matter whether you're doing one of these kind of simple analyses or what. Okay, next we're going to do the analysis. So let's do the analysis here. Okay, so to maintain the temperature at 20 degrees C, we're going to have to put in... we're given QH, right? So QH is, let's just put down what we know here. QH is equal to 3 times 10 to the 6 kilojoules, right? And then we're going to also say TH is equal to 20 degrees C. This is 293 Kelvin. Remember, if you're using these ratios, you have to use Kelvin, okay? You can't use Celsius. We're talking about the Kelvin scale. All right, so make sure you use Kelvin. Okay. All right. So then we're going to require that we're going to use this ideal analysis that the heat pump max theoretical is equal to TH over TH minus TC, which is equal to QH over work of the cycle, which equals QH over QH minus QC, right? And then so we're going to say that so we're going to say here essentially that we need to have QH, we need to have, let's see, well, we can say it this way. So QH to the Q side. So we actually need to have this be greater than or equal to, right? So this actually has to be greater than or equal to this. For an ideal cycle, it's an equality, right? Okay, for an ideal cycle, it's an equality, but we need to have this, right? In general, we need to have greater work input than the ideal work input for a heat pump. So then in the end, what we're going to get is that QH times TH minus TC over TH is greater than or equal to the work of the cycle. And we're going to calculate the equality, right? Because we're trying to figure out what the minimum work is. So the minimum work is the equality, right? So if TH is 20 degrees C, we can get that you're going to have like you're going to just plug in the numbers here. If we just plug in the numbers, so example 1 continued, you're going to have here 3 times 10 to the 6 kilojoules divided by TH, which we already know is 293, times 293 minus TC. Just kind of rearranging that equation a little bit, but okay. And that has to be less than or equal to the work of the cycle. And we can say it's equal to the work of the cycle min. Okay? All right, so for part A, all we have to do then is plug in the numbers of the different reservoirs. Okay, I'll tell you what I was just thinking here in a minute. Let's just finish the analysis. So 288K, 288K. And so this is 3 times 10 to the 6 divided by 293 times 293 minus 288. And this ends up being 512 times 10 to the 4th kilojoules. Okay, so that's part A. Now if we do B, if we do the same thing, so TC is equal to 283. It's a little colder. And then we get work cycle min is equal to 10 point, I'm just going to give you the final answer, okay? I'm just not going to plug in the numbers over and over again. 24 times 10 to the 4th kilojoules. Whoa, it's pretty substantial, right? It's actually double. It's actually double. All we did was increase the temperature by 5 degrees Celsius, and it's that much more work that's required. That seems pretty significant. And then C, we have TC is equal to even lower, 278. And work cycle min equals, I just put a box around our answers. Work cycle min is equal to 15.36 times 10 to the 4th kilojoules. All right, so that is, I mean, that's pretty major, I think. I mean, essentially, you got yourself really a 3x temperature, 3x temperature, a 3x work input for every 5 degrees lower temperature. And this is the problem when you get to heat pumps, say for electric cars. And so if you have an electric car in Minnesota and has a heat pump, the power requirements just go through the roof because the minimum work requirement for a heat pump to operate with colder and colder ambience to maintain the same temperature inside the cabin is too much. You might as well just spend electricity to do a hairdryer, like our hairdryer experiment, to heat that up. The other thing that I want to note is that you have these 3 different cases: the ground, the pond, and the outside air. Heat exchangers have different, what we call heat exchange coefficients between different gases. You'll learn this and when you get into heat transfer, but essentially transferring heat with a pond is a lot easier than transferring heat with the outside air. But okay, that's neither here nor there. We're just going to assume they're thermal reservoirs and the heat transfer is perfect. But anyway, so what I'm just going to say as conclusion is that you have for every, we'll just say for decrease outside temp of 10 degrees C, we have 3x work required. Right? Okay, that's pretty significant. Okay, so that's that example. The next example that I want to do is about the Carnot cycle. Okay, so here's the next one. Essentially, Carnot cycle has the same the way you have to think about Carnot cycle is it's a physical embodiment of an ideal reversible power cycle. Okay, so when I say Carnot cycle, I mean it's like an embodiment. It actually has processes in it that you can imagine would be reversible and ideal, adiabatic and reversible. So when I say ideal reversible power cycle and Carnot cycle, by the second law, they have to have the same maximum thermal efficiency. That's 1 minus T over TH, okay? But when I say Carnot cycle, you might think of a certain set of processes, right? So in this case, we have an example. Gas within a piston cylinder assembly executes a Carnot cycle during which the isothermal expansion occurs at TH equals 600 and the isothermal compression occurs at 300. So that essentially means those are the temperatures at which you're exchanging, the reservoirs you're exchanging heat with. Determine the thermal efficiency, the percent change, and et cetera, et cetera. Okay. We did do a Carnot cycle. Here's what I'm going to do. Let's do it this way. So I'm going to first say known. We're going to say gas in a piston cylinder. We'll say executes a reversible Carnot cycle. All right, and what we need to find for these different situations, we need to find thermal efficiency. We'll just call that eta, okay? And then we need to find, and then we need to see changes in eta. So we need to find different um, the percent change in thermal efficiency. So we need percent change in eta for different percent change in thermal efficiency TH and TC according to the A, B, and C, D that we have to do. Okay? All right, so let's see. I think the first thing is that we have to assume that we have a Carnot cycle. So I'm going to assume ideal Carnot cycle. We don't need to necessarily assume ideal gas because it's an ideal Carnot cycle. And we could say ideal gas, but I mean, it doesn't really mean much. Ideal Carnot cycle, I guess it's operating between the, we'll say, thermal reservoirs. At, what is it, 300 and 600. 300K and 600K. All right, so this just means that like you have an ideal. So if you have a diagram, you have a ideal Carnot cycle in here. We're just going to say it's a piston cylinder. Well, let's just draw it. We'll just draw the piston cylinder. So you have this piston cylinder in here that operates according to an ideal Carnot cycle. It's moving up and down. The piston's moving up and down and it executes a cycle. This is our thermodynamic diagram right here. So this is the system. It is exchanging heat with, we'll just say it's exchanging heat. This is the work. This is QC and QH. Okay. Now it's exchanging heat with two reservoirs. So this is TH and this is TC. So we're assuming that the temperature here is perfect, that there's no heat transfer coefficient or anything like that. So the temperature that the cylinder reaches is the same as the thermal reservoir. Okay. So that's essentially what I mean. Like if we look at the what did we have before for the diagram for this? Where is it? Carnot power cycle. Here it is right here. So I'm just going to draw out my PV diagram. You can see it here in a nicer way. I'm just going to make sure I copy the lines better. Okay. 1, 2. Sorry, you're not seeing my scribbles right now, but you will in a second. 3. Oops. Undo that. Undo that. Okay, so there's 1, 2, 3. Oops. Sorry, you can't see what I'm doing here. 4. All right, so then TL over TH, so this is TC and TH. Okay. So let me go back. Okay, so here we go. So here's my Carnot cycle, right? It's nice to make a PV diagram. So this is P and little v. Oh, a little bit messy. Well, it's not so good, but okay, here we go. So you get the idea, right? It's operating between TC and T. This is really bad. All right, so anyways, that's the deal. So it's operating between these two isobars, right? So this is a T equals constant bar. This is the compression. This is the expansion. So pressure's going up, pressure's coming down. So those are the two processes that we have. Okay, and so for this ideal Carnot cycle, I don't know how this actually works, right? I don't know how you do an isothermal compression expansion, and then you have these other processes, but in real life, it's really difficult to achieve. But and if you can do it, you might make a lot of money. So who knows if you can be the next one to design a Carnot cycle. We'll be talking about the Stirling cycle, which is about as close as you can get to the Carnot cycle in terms of idealized efficiency. But in practicality, isothermal compression expansion is really a tricky situation. Okay, so analysis here. So let's do part A. So part A, so the analysis is essentially that we have efficiency equals 1 minus TC over TH. Okay, oops. Okay, so that's essentially, that's the analysis, right? So if we want to see like TH equals 600K and TC equals 300K, which is the baseline, right? Thermal efficiency is equal to 1 minus 300 over 600, and you can guess what that is, 0.5, okay? So it's 50%. Okay? Okay, now if we went B, and the first thing it says is what happens if we, first thing it says is what if we increase TH by 15%? So TH is then equal to 600 times 1.15, which is equal to 690. TC remains at 300. And we have thermal efficiency equals 1 minus 300 divided by 690, which ends up giving you 0.565 or 56.5%. And it's a 13% increase. Okay, so it's a pretty significant, you increase the temperature by a little bit, 690, about 90 degrees C, you can really get a significantly higher ideal Carnot cycle efficiency. So see, this is going to get repetitive, so I may not have to do all these. So the percent change in thermal efficiency when TC decreases by 15%. So this we have TH equals 600K. Put my units in here, and TC equals 0.85 times 300, and this ends up getting, so we'll just call this B and C and A, is equal to 0.575. So we've increased the thermal efficiency by making the TC colder. That's interesting. Now, this kind of goes to the zero motor a little bit. It's a matter of selecting the exact right TC. Usually, you have no choice what TC is in a cycle on Earth. It's whatever the cooling tower temperature is. The ambient temperature is usually the TC. You can't mess around with, in the zero motor, they're trying to make the TH the environment, and you needed to have some TC that was lower than that, right? Well, where are you going to find anything that's lower than that? You might be able to find something that's colder, like the air is hot and the water is cold, and you can try to operate a cycle between those two things. That's possible, but your work output is going to be extremely low, right? Okay, so I don't know if anybody thought of that when they were thinking about the zero motor, but okay. So this is a 15%. No, I'm sorry. It's a wait. This is 565. This is a 13%. This is a 15%. Sorry. This is a 15% increase. Okay. Now D is when you have, let's see, what is D? D is essentially when you've got a percent change in thermal efficiency if so you have TH increasing and TC decreasing. So in this case, you've got TH is equal to 690 and TC is equal to whatever we had there, which was 255, right? And then you're going to get something like this, and D is equal to 0.63, and this is a 26% increase. All right, so it's kind of additive, right? 15 plus 13. Not quite, right? 15 plus 13. But you get a much bigger increase. So essentially, increasing the range of temperature between TC and TH, whether you're lowering TC or increasing TH, you can get a higher ideal thermal efficiency of your ideal cycle. Okay. Okay. Good. Hopefully you understand that, and you can work some examples. I'll give you some homework to work on with regards to that stuff soon, or for Monday over the weekend. I won't make your homework assignment for Monday as intense as the experiment that you did last weekend. And I'm sorry if I gave you too much to do for the weekend, but I think it was pretty interesting. Hopefully you did too. Okay, great. So now let's see, where am I talking about here? Oh, here we go. Now, the last thing I want to talk about in this chapter is what's called the Clausius inequality. The Clausius inequality is the basis of what we will start talking about Monday with respect to entropy. Okay? The Clausius inequality is applicable to any cycle without regard to bodies from the system undergoing a cycle. This is setting us up for calling entropy a thermodynamic property, essentially. Receives a heat transfer or to which the system rejects energy by heat transfer. Such bodies need not be thermal reservoirs. It only depends on the heat transfer leaving your whatever you define thermodynamic system boundary. And the Clausius inequality is only a function of the heat transfer, not a function of the work. Okay, so the Clausius inequality, which you're going to see a little bit more and stated in different ways, looks like this. So it's developed based on the Kelvin-Planck statement of the second law and can be expressed as for a cycle, the change in energy or the change in heat over the temperature at which that heat is conducted through the boundary of the cycle, for the boundary of the system. So, like, remember we did the Stirling engine, or I'm sorry, the Carnot engine, and we saw that we exchanged heat. Let me just show you. So, like, for instance, example 2, we had this boundary, right? So the boundary that the heat transfer occurs right here. So this is the boundary, right? Through which that heat transfer goes. And that's what we're talking about. So that B is a boundary over all parts of the cycle. So, like, this has to be summed over the different parts of the cycle. So if you made this into a sum, and this means just over the course of a cycle, whatever that system is doing inside, what are the net heat that comes out, dq, over that cycle, at what temperature does that heat transfer occur, is equal to some negative sigma. The sigma, you might think, okay, what the heck is this sigma? Right now, this eventually is going to become entropy. Right now, we're going to assume that this sigma means like the strength of the inequality or the strength of the equality, right? So how essentially irreversible is this system? That's what we're gonna try to figure out. Okay, the Clausius inequality is developed based on the clause of the second law, as I said before, and the nature of the cycle executed is indicated by the value of this sigma. Okay, so sigma cycle equals 0. If it equals 0, there's no irreversibilities present within the system. All right, it's the reason why it's negative is because sigma has to always be greater than 0. So the negative just reflects the sign, because if there's heat coming out of the system, we define it as negative. Just remember that, okay? That's just why it's negative. So there's like weird negative, positive stuff going on. Okay, if sigma of the cycle is greater than 0, that means that there's irreversibilities in the system. And if the sigma of the cycle is less than 0, then it's not possible, okay? You can't do it. Okay, that's essentially it, right? So let's just think about this equality for a minute. What does this really mean? For the cycle, essentially what it means is that for all the different boundaries B, this heat transfer through at different temperatures has to equal some sigma here. So that's what we're going to try to figure out. So let's, as usual, and I think what people like the best is if we do an example of this, right? So let's finish off today's lecture by essentially doing an example of this Clausius inequality and see if we can't get to the bottom of it. I'm not going to dwell on Clausius inequality in this form too much because I don't want to confuse you, because essentially we're moving this right into entropy, and this sigma right here is essentially just like entropy. It's essentially what you think entropy is. Okay, so here's an example that they came up with. This is the textbook. I took this right from the textbook example. So this system undergoes a cycle receiving 1,000 kilojoules of heat transfer at a temperature of 500 K, and discharging 600 kilojoules by heat transfer at different temperatures, A 200, B 300, C 400. What's the nature of the cycle? That's kind of a weird question. What's the nature of the cycle? The nature of the cycle is it reversible, irreversible, or is it impossible? That's really what they're trying to ask, right? And so you can guess there's 3 different temperatures. One of them is going to be one of each. Okay, that's what's going to happen. Okay, to determine the nature of the cycle, perform the cyclic integral of the Clausius inequality to each case and apply the second law. So that's what we're going to do. We're going to use the Clausius inequality to decide whether these things are possible or impossible. Okay? I mean, one could also say do this in another way by using the, well, let's see, could you do it? Yeah, you might be able to do it. If you say 600 kilojoules and heat transfer, so you could maybe come do it in a different way, but we're going to use the Clausius inequality. All right, so here's how you do it. I've been using the wrong slide format the whole time, and hopefully that's not annoying to people, but that's better, right? Sorry about that. Okay, so anyway, so here we go. The example goes like this. So for each cycle, we have, and I'm just going to take you through this. So like the dq over t, the cyclic integral, is equal, so imagine the Carnot cycle, right? At different parts of the cycle, it has different heat, right? So like when you're going through isothermal expansion, you have heat out of the system, and when you have isothermal compression, or I'm sorry, expansion, you have heat into the system, and when you have isothermal compression, you have heat out of the system. So that's what we're talking about. So that's why it's over a course of a cycle, because you're imagining like the piston cylinder configuration. So at some point of the cycle, you've got Q in over TH. So that you have this Q in over TH, so we have to include that. Minus Q out over TH. So Q in is positive, right? Heat into the control volume or into the thermodynamic system is positive. Heat out is negative. So we have Q in over TH minus Q out over TH. Okay, equals negative sigma of the cycle. Now, in this case, so 1,000 kilojoules divided by 500 kilojoules, 500K. So 1,000 kilojoules over 500 and 600 over 200. So this is, if I go back here, receiving 1,000 kilojoules, 1,000 kilojoules transfer at 500 and 600 kilojoules at these different temperatures. What do we get? Okay, we get the file. That's not what I want to do. Get back here. Okay. So we have essentially then we have 1,000 over 500 minus 600 over 200, and we get negative 1 kilojoules per kilogram, which means that the sigma is positive. Beautiful. So we assume sigma positive means that there are irreversibilities in the system. It's a possible system, so a thumbs up on the system, but it's irreversible, right? The meaning that we don't have a cycle that's operating at the Carnot limit. Now, if we have B, we have 1,000 over 500 minus 600 over 300, which is the new TC for part B, which is equals to 0. Sigma is 0. When sigma is 0, it's a reversible cycle. Okay? That means that that thing is no irreversibilities present in the system. It's a perfect Carnot cycle. If you have C, where you have now 400, so you have a higher temperature, at TC, and you make the same amount of work and heat, and you have the two different heat rejections. So you could very well think about that. Then you would say, okay, then you have 0.5 kilojoules per kilogram, and negative sigma is equal to, sigma is equal to negative 0.5, which is impossible, right? You can't have that situation. Okay, so now, let's do a quick example here before we quit, and then we can move on with our weekend. Okay, the steady state data listed below are claimed for a power cycle operating between hot and cold reservoirs at 1,200 and 400K respectively. For each case, evaluate the net power delivered, developed for each cycle in kilowatts, and the thermal efficiency. Also, in each case, apply the Clausius inequality on a time rate basis to determine whether the cycle operates reversibly, irreversibly, or is impossible. Okay, let's do this. So this is the last one. This is so we have these different things. I'm going to put this on my tablet here, and we're just going to go. All right, so here we go. So what's known about this? So what's known is that we have steady state power cycle between two thermal reservoirs, hot and cold reservoirs. We're supposed to find, in this case, we're supposed to find each case, apply the Clausius, determine whether the cycle. We're supposed to find the work developed, so work of the cycle. the thermal efficiency of the cycle, and whether we'll call it, as they said in the last example, the nature of the cycle. Okay, and the assumptions. The assumptions are that we're operating the cycle, that we have a steady state cycle. So one is we'll just call it one steady state cycle. Two, we're going to assume that that these are perfect reservoirs, that the heat exchange occurs at the temperature of the reservoirs. Okay, I think that's pretty much it. We don't need to make many more assumptions like that. Am I missing anything? No. Yeah, we're going to normal sign conventions. So the diagram looks like this. We're going to have hot reservoir, cold reservoir, some cycle operating here. We have work. They say use the time. Yeah, kilowatts. So we're going to use the dot. Doesn't matter. We can make a sigma dot. I hope you're okay with that. We're making a sigma dot. So this is TH. This is TC. We've got heat going in here. It's a power cycle. QH and QC. Right? Our thermodynamic system is this one. So this is our system. Right? And then I think that's all we got to do for the diagram. So this is pretty straightforward, right? It's a Carnot cycle with QH and QC. That looks like 6. Let's get rid of that. It's TC. Okay. So let's go. So number of things that we need to calculate, but they're pretty simple, right? So the analysis, let's just do A first. So work of the cycle. We're just going to say work. We're just going to say call W. You don't have to say cycle. Let's see. Work is equal to QH dot H minus Q dot C. Okay. And do we have QH and QC? We do, right? Let's see. Yes, QH and QC, 600 and 400. So is equal to 600 minus 400, which is equal to 200 kilowatts. Okay, so we've got that. The efficiency of the cycle, so I'm just going to box that. The efficiency of the cycle in this case is equal to work of the cycle over QH dot. That's a dot. So my kids are downstairs. You can hear them, I'm sure. It's Thursday evening and they're on spring break, as I said. So all bets are off in the noise situation. Let's see. So this is equal to 200 divided by 600 equal to 0.33. So we have 33%. 0.3% is 33. 33%. Now, let's see. If we're going to determine, so this is example 3 continued. So example 3 continued, we have something like sigma of the cycle. Oh, we'll just call it sigma. Let's just call it sigma, okay? Sigma equals, we'll call it sigma dot, because we're doing things on a rate basis, which is okay. We can do things on a rate basis. Equals Q, well, so negative sigma equals QH over TH minus QC over TC. But in this case, we have QC dot over T. My C's are looking like QH over TC minus QH minus TH. And this is equal to, now we have the temperatures and we have the heats. So we can figure out whether the cycle is possible or not. So 400 over 400 minus QH, which is 600 over 1200. And this ends up being 0.5 kilowatts per K. So the units of sigma are kilowatt or kilojoules per K or kilowatts per K in this case. So what do you think? Is this cycle possible? Think about it based on what we said. What What direction is it? It's positive, right? So this is an irreversible cycle. Irreversible cycle, because the sigma is greater than 0. Okay, so let's do B. So B is that we have QH equals 600 and QC equals 0. Uh-oh. We already know what the answer to this one is, right? QC equals to 0. Give me a break. Shouldn't have. This is silly. Okay, anyways, B. Just think to yourself. Just think to yourself what the answer to this one is going to be. Can QC be 0 or not 0? Think about it. 600 minus 0 is equal to 200 600 kilowatts equals W dot. Okay, so the work equals a whopping 600 kilowatts, and the thermal efficiency is equal to work of the cycle over heat in, so that the thermal efficiency is then equal to 1. So this is equal to 100%. Okay, and then let's just do this sigma dot thing equals QC, which is 0 over 400 minus 600 over 1200, and this is equal to negative 0.5 kilowatts per K. So this is the answer here. I'm just gonna underline these, okay? So this is impossible because sigma must be greater than or equal to 0. Must. Right? Okay, so impossible. We already knew that though, because you can't exchange heat with only one reservoir and make work, right? That violates the second law. Good. You learned that already. Hopefully you guessed that when we just started this. Okay, the third one is QH equals 600 and QC equals 200. All right, so Q dot H minus Q dot C equals, what did I say, 600 and 200? So 600 minus 200 equals 400 kilojoules, kilowatts, equals the power that you get out. And then, so the thermal efficiency then is equal to, so this is in part C, we'll call this B, B, B. I'm just going to give these names so that we know what we're talking about, A and A. So this is Q, this is the C, the third one. So this efficiency then, if you do the math on this, work over the, so W dot of C over QH, which is equal to, in this case, it's equal to 66.7%. That's pretty high efficiency for a power cycle, okay? That's a pretty awesome power cycle. Let's see how awesome it is according to the second law. And so what we'll do is here, we'll just do sigma is equal to, of C is equal to 200 over 400 minus 600 over 1200. And this is equal to, 2 over 4 is 1/2, this is equal to 1/2, so this is equal to 0. So this is a, reversible power cycle. So it's a reversible power cycle. Great. So essentially, this is a perfect power cycle. Not achievable in real life, but this is the maximum that you could possibly expect, given these two thermal reservoirs, what you could get out of the power cycle. Okay, so now we could have done this using kind of the other analysis that we did with the Kelvin-Planck statement, but we don't have to do that. Now we have this sort of tool, this Clausius inequality that we can use to evaluate the whether these cycles are possible, right? So hopefully you understand that and you can get through it. I'll give you a couple homework problems to work on tomorrow or through the weekend, and excuse me, you can do your best. And if you have any questions, of course, always write me an email. Let me know if you have any concerns or questions about the problems or second law. Don't worry if you don't understand the second law, because we're going to get more into it as we go in the next chapter. Okay, have a great weekend, and I'll talk to you on Monday. Bye.